In this lecture, I just wanted to describe an implementation of the one-time pad encryption scheme. Now, there are two reasons why I'm doing this. First of all, I find that for many students, an abstract description of an encryption scheme or a crypto system in general is sometimes difficult to understand. And very often, by seeing a concrete example or instantiation or implementation of a crypto system, it provides another way of understanding the material. It also allows students to take the given implementation and then play with it, modify it, make it their own, see what the changes do, and explore things and learn things in that way. The second reason I wanted to do this is because it gives us an opportunity to look at some implementation level details that arise. And in particular, we'll see how random number generation comes into play as we talk about the implementation. Just to remind you, in the one-time pad encryption scheme, we have a message space consisting of all n-bit strings for some particular n that has to be specified as part of the scheme. Key generation chooses a uniform key of the same length. That is, it chooses a uniform key, which is an n-bit string. Encryption of the n-bit string m with the n-bit key k is done by simply XORing those two n-bit strings together to produce the ciphertext. And decryption just reverses this process and XORs the n-bit key k with the n-bit ciphertext c to recover the original plaintext. Now, I've implemented the one-time pad encryption scheme in C, and this was done mainly for convenience. C provides me with low-level bit string manipulation primitives. In particular, it allows me to compute the XOR of two bit strings in one operation, very conveniently, more conveniently than in a language like Java. Now, of course, you can implement the one-time pad encryption scheme or really any crypto system in any language, and it's ultimately your choice what you want to implement in. But I find C to be convenient as it allows me a greater measure of control over what I'm doing. We talked a little bit about this in the last lecture, but I want to just fix some ideas and mention the particular kind of data representation that I'm going to be using. So ultimately, we're going to be writing programs that read the input from a file. So they're going to read, say the encryption algorithm is going to read the plain text from a file and the key from a file, generate a ciphertext, and write that to a file. And we have to make some decision about how we're going to be representing the data in those files. The plain text file is represented using really the natural format. That is, we're going to just use ASCII, plain old ASCII files as our plain text, and that's going to allow us to really encrypt anything we like, which is always ultimately represented in ASCII. The key and the ciphertext are going to be represented in hexadecimal, and as described in the last lecture, we're going to make the choice of writing those hexadecimal values to a file in ASCII. So this just means, again, we have to be a little bit careful in our programs as we read to and write from the file to make sure that we're expressing the hex digits appropriately in the ASCII representation. But this will allow us to be able to read the files from the command line or using a standard text editor, which I find, again, is a convenient choice. So let's talk first about the key generation algorithm. Now, when we describe our algorithms, both in general as well as in the particular case of the key generation algorithm for the one-time pad, we will generally assume access to uniform random bits. Right? When we described the key generation algorithm a moment ago, we said that the key generation algorithm chooses a uniform n-bit string. Well, where do these random bits actually come from? Somehow or another, we need to obtain them. And this brings us to the topic of random number generation. It's a bit difficult, actually, to imagine generating numbers, random numbers, on a computer. A computer, after all, is a deterministic device. If you feed it some set of inputs, it will always run some program you give it and produce the same set of outputs, and there's no choices or non-determinism inherently in that process. Nevertheless, we can obtain in practice random numbers using the following two-step process. First of all, what we'll do is continually collect a pool of high entropy, or in other words, unpredictable data. Then when random bits are needed for some program, what we'll do is we'll process this data to generate an independent and uniform sequence of bits. If insufficiently many random bits are available, right, if the system hasn't collected enough high entropy data, then the request for random bits may block until sufficient entropy is available. Both of these steps are handled for you automatically by the underlying operating system, and so they're not something that the programmer has to directly worry about, other than knowing the appropriate call to make in order to access those random bits. One comment I want to make here is that the term high entropy actually does have a precise technical meaning. However, I'm not going to get into that in this course, and so for now you can just equate the term high entropy with something having a high level of unpredictability, something whose value you can't easily predict. So let's look in more detail at step 1. I said that what is going on continually is that a pool of high entropy data is being collected. Well, where does this high entropy data come from? Ultimately, it has to come from something external to the processing chip itself. Very typically, this high entropy data comes from external inputs that have some measure of unpredictability. So for example, delays between network events, or times required to access data written to the hard drive, or keystroke and mouse movements made by the user. In particular, the inter-keyspace, the keystroke dynamics, looking at the times between consecutive keystrokes by a user, do have some measure of unpredictability. I want to make clear here that the data that's collected by any of these events, or from any of these events, is not uniform. If you ask a user, for example, to move their mouse around on the screen, or their cursor around on the screen, then typically what the user will do is draw a small circle or perhaps move the mouse back and forth, but it's not going to be done uniformly across the entire screen. Typically there'll be a pattern, either a circle or a back and forth motion, and moreover, consecutive positions of the cursor on the screen are almost surely going to be very close to each other. So this is why we need that extra step, step 2, in which we process this data to obtain a sequence of independent and uniform bits. In addition to collecting this pool of high entropy data from external inputs, more recently, manufacturers have built or have included hardware level support for random number generation. For example, Intel produces a line of chips in which there's a physical process going on the chip itself that provides a source of unpredictable data. In pictures, then, we can view the entire process of generating random numbers in the following way. What we have on the screen here is a representation of our pool of high entropy or unpredictable data. Right now it's empty. As some external events occur, let me say it differently. At some point, a program may request random bits. At the present moment, there's no unpredictable data in the system, and so that request will block. That is, it will hang until such point in time at which the operating system can respond to the request with a sufficient number of random bits. How does this pool get filled? Well, we said on the previous slide that there may be external events that occur that have some measure of unpredictability, and those will be recorded in our entropy pool, building up, as it were, the entropy or the unpredictability in that pool. At this point in time, the pending request we have for some random bits can be answered, and that will lower the available amount of entropy or unpredictability in our pool. Note here that, as we said on the previous slide, we can't take the bits as they are from the pool and return those to the user, because they're not going to be uniform and they're not going to be independent of each other. So this is where step 2 comes in, some form of processing of that unpredictable data, also sometimes called smoothing, to result in a sequence of uniform and independent random bits that are returned to the calling program. Now, the precise details of how this is implemented depend on the system on which you're running. In Unix, which is the example I'm going to be using for my implementation, a program can read or can access random bits by reading from the file dev_random. And we'll see this in the example that I give in just a moment. Very often, crypto libraries that you might be using also provide you with a mechanism for obtaining sequences of uniform bits. So let's look at how the key generation procedure will work. So I've implemented, as I said, the algorithms for the one-time pad. Here we have the algorithm I've written in C for key generation. So let's look up at the top of the screen where I have a parameter called len here that I've defined equal to 12. So this corresponds to the integer n that we had in our description of the one-time pad on a previous screen. So this allows the programmer to specify the value of n by simply changing this line at the top of the file. Now I don't want to get into specifics of the C programming language, but I do just want to walk through some of what I'm doing here. So the interesting thing here is that I'm just defining two file pointers, one that's going to be reading from what I've called rand file, and one that's going to be writing the key to a file that I've denoted here by out file. We initialize the rand file by opening up the file devrandom that I mentioned a moment ago for read access. For the out file, we're going to open a file that I've chosen to call key.txt and with write access to that file. And then we do some kind of standard error checking over here that you don't need to worry about if you don't really understand it. Then we have a loop here where for I equals 1 to len, right, up to len number of bytes, we're going to be reading a byte from the rand file, i.e. from devrandom, and then writing that byte to our key file, key.txt. The precise characters here are specific to the C language. Again, it's something that's not really important and that I don't want you to worry about because it's a language-dependent feature that has nothing really to do with cryptography. Now I've compiled the program, and we can try running it. So we've run it. It's read a sequence of random bits from devrandom and written them to key.txt. And so we can look at the value of the key. So what we have here is a 12-byte key. We're expressing it in hexadecimal. So we should have 24 hexadecimal characters, which we do. And what I want to show you here is that if I run key generation twice, I obtain a different key. Each invocation of the algorithm gen, or of the program gen, is reading from the devrandom file, which we can view as giving access to a sequence of uniform and independent random bits. So we expect, therefore, that every time we run the gen algorithm, we're going to get a completely random, uniform, and independent key from the previous time. Let's look next at encryption. So remember that a plain text is going to be represented as a sequence of ASCII characters, and the key, as we just saw a moment ago, is written to a file as a sequence of hex digits, though written in ASCII. What encryption needs to do is simply read from both of those files and XOR the resulting values in order to obtain the ciphertext. Let's see how that looks. So here we have the encryption file. Notice that I've set the value of the len parameter to 12, which is the same as before. So here I'm opening up three files. A key file that corresponds to key.txt, where I've just placed the key. A p file, which is going to be reading from a file ptext.txt, which is where the plain text will be located. And then a c file corresponding to the file ctext.txt, which is where we're going to write the ciphertext. And then what we do is simply have a loop that for I equals 0 to length minus 1 is going to read a byte from the key file, read a byte from the plaintext file, XOR them together. So here the caret character is allowing me to do XOR of a single byte in C. It's again a language-dependent feature of C. And then I write the resulting value to the ciphertext file, C file. So we can see, for example, I've precompiled the program. And if I look at what I have in my plain text, I have a hello world. If you count the number of characters there, making sure to count both the space character and the final exclamation mark, you'll see that we do indeed have 12 characters. We have our key file that we've generated before. And if I now call encrypt and look at the resulting ciphertext, well, I have some hexadecimal value, some ciphertext represented in hexadecimal. Okay. Now, one thing I want to show, I want to load here a key that I've defined before. And encrypt. And I want to just now walk through and just show you that this is actually giving us the correct result. So again, we have the plain text, we have the key, and we have the ciphertext, right? The ciphertext is different from what we had before because we're encrypting using a different key. And now if we want to verify correctness, right, remember that the first character of the plain text was a capital H. If you look at an ASCII file, if you look at an ASCII table, you'll see that that corresponds to the hex value 48, which corresponds to the byte 00100100. If we go back and look at our key, you see that the first two hex digits of the key were 95. The hex value 95 is equal to the binary value 01010011. If we take the XOR of this 8-bit value and this 8-bit value, and just do that bitwise, then you can confirm for yourself that their XOR is this 8-bit value here. Converting that back into hex, we see that that's equal to the hex number DD. And indeed, if we look back here, we'll see that the first two hex characters in the ciphertext are indeed DD, and everything matches up. And you could similarly check that for every subsequent character of the plain text, and every subsequent pair of hex digits in the key file, and pair of hex digits in the ciphertext. Finally, we come to the decryption algorithm. Decryption is simply the reverse of encryption. What we do is we simply read the ciphertext and the key. Now they're both going to be represented in hexadecimal rather than ASCII. And we then XOR them to recover the message. And I can just walk you through that here. We have our decryption file, which again is reading from the key file, writing to a different plaintext file so we don't overwrite our initial plaintext, so I just called it ptext2, and then a ciphertext file. And similar to before, we have a loop here that loops over characters of the, or rather pairs of hex digits, if you like, from the key and the ciphertext, XORs them together here, views those back as ASCII characters, and writes that to our plaintext file ptext2. And if I call dec and look back at our plaintext file ptext2, we see that we got back the original plaintext that we started with.